so that's my first. And now I'm gonna go quickly. Okay, so looking at these beanbag setups, we can go to the starting position. So that's this meter stick. And then looking at the beanbags and how they're spaced, and we can give this view as well. And you count how many beanbags you see in the same amount of space. The blue beanbags, when I was moving faster, extend much farther than the red ones. All 4 of those are within 2 of the blue beanbags, and then the other 2 blue beanbags are out here. All right, so please open up in your lab notebooks with me and go to a blank page and label it as motion maps. So we are going to recreate what we just saw with the red and the blue beanbags. So reminder, the red beanbags were slow and the blue beanbags were fast. And both of these started at the same position. So this is our start. And then all of these beanbags were dropped once every 2 seconds. So our slow beanbags we saw were spaced out pretty close together. And then within 2, really all of our other beanbags were. So within 2 of the blue ones, all those red ones pretty much were in that same space. So this is like our classroom. And then each one of these, so this is 0 seconds. And so is this. This was 2 seconds. This was 2 seconds. This was 3 seconds. Or sorry, 4 seconds, because we're going every 2 seconds. This was 4 seconds. This was 6 seconds, because there was another 2 seconds. And then this one was 6 seconds. So when we think about in terms of time, 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. So these 2 objects are moving at different speeds, which is reflected by this distance. The blue beanbags are spaced farther apart, which meant that I was moving a farther distance in the same amount of time in 2 seconds compared to this red beanbag. And so what we're going to add to our motion map to really emphasize that difference in velocity is these arrows that represent velocity arrows. This one would go off our page. And because this red car is moving a lot slower, those velocity arrows, those vectors, need to be a lot smaller. And now I know what direction I'm moving in, and these tick marks just mean congruent. They mean that this velocity is constant throughout time. And what does this look like when our object is speeding up? So let's do a new motion map. This is what motion maps look like for constant velocity. Let's do speeding up. And let's change it up, and instead of moving to the right in the positive direction, we're going to move to the left in the negative direction. So I'm going to start with a dot, so that's my 0 seconds position. And if I'm speeding up, think about what is going to need to happen to the distance between those dots. In other words, am I going to be traveling farther every second if I'm speeding up, or less far every second if I'm speeding up, or the same distance every second if I'm speeding up? So I should, if I'm moving faster and faster, cover a farther amount of space, like more space in the same amount of time. So this might be 1 second, then in the next second, I've traveled not this much, but even more than that. Then I'd travel even more than that the next second. So this is like 0 seconds, 1 second, 2 second, 3 second, and even more than that in 4 seconds. So again, I'm going to add these times just to help me. And then I need to add velocity arrows. So my first velocity arrow needs to be pretty small. My next one should be a little bit bigger. And because I'm speeding up, my velocity vector should get bigger and bigger and bigger every second. And that's represented by the length of the arrow. Now, I'm also going to add my acceleration arrow. And my acceleration is going to tell me how my velocity is going to change. So acceleration almost kind of predicts the future. And so when I look at this arrow compared to this arrow, I want to think when I'm adding my acceleration vector, do I want to stretch my arrow to become this? Or do I want to shrink my arrow to become this? And to go from here to here, I want to stretch it. So that means my acceleration needs to point in the direction of stretch. So I'd pull on my arrow in this direction to get it to stretch to be this size. Now I'm going to do that again. To go from this arrow to this arrow, this velocity to this velocity, I would want to stretch it again in this direction to lengthen it. Now again, to go from this vector to this vector that represent velocity, I would want to stretch my velocity vector. Same thing. What about slowing down? If I'm slowing down, instead of having my position become closer and farther and farther apart over time, right? So I'm traveling farther and farther every second. Instead, I'm going to travel less and less every second. So I'm actually going to start my motion map, and we're going to call this 0 seconds, with a pretty substantial difference in position between 0 seconds and 1 second. Then between 1 second and 2 seconds, I want to make this actually smaller. So I'm traveling less distance every second. Then at 3 seconds, I'm going to want even smaller. And then at 4 seconds, even smaller. So again, I'm going to add those velocity vectors, and because I'm slowing down, should those velocity vectors become smaller? Should they decrease in length over time? Or should they increase in length over time if I'm slowing down? My velocity is getting smaller, so my vectors should also become smaller. And maybe I'm not even moving at 4 seconds. If I'm not even moving, I'm not even going to draw a velocity vector. Okay, now let's add our acceleration vectors. And so these, just as a reminder, the green is the acceleration vector. So it gives you the direction of acceleration and the magnitude. So if I look at this motion map, from 0 seconds velocity to 1 second velocity, just like I did up here, I'm going to think like, would I want to stretch my vector to get this one? No, I'd want to like squish it. So I'm going to push on this arrow this way to make that velocity change. I'm going to go the opposite direction of that velocity to make it change to become smaller. Same thing from here to here. I'd want to shrink my arrow. Same thing from here to here. I want to shrink. And then again from 3 to 4 seconds. And then we're going to add one to that last second. And the reason why we can look at that change in velocity over change in time to determine the direction of our acceleration is because acceleration is the change in velocity over change in time. So in this example, when my velocity is becoming smaller, that means my acceleration should be in the opposite direction because my velocity is changing in the opposite direction. So when we're slowing down, we can see this pattern of velocity and acceleration in opposite directions. And with speeding up, velocity and acceleration are in the same direction. So just a reminder, these green vectors represent acceleration. These pink vectors represent velocity, both in magnitude and direction. So the length tells us how big they are, and the way the arrow is pointing tells us how the direction. And I'm also going to add some outlines to these dots because the dots are also a really important part of this motion map. The dots are like the bean bags in our experiment. And the dots represent the position at a moment in time. And that is how you draw a motion map.